Now it's time to start actually mounting practical attacks to the systems that are most probably will be included into the target scope. So in this section we will review so-called system and network attacks, right, against Windows and Linux operating systems and the services that are run on them. And in the next section we will review web application and web server attack techniques, and in the third section from this one we will review social engineering attack vector. So these three are the most common within pen testing disciplines. So the methodology remains the same after enumeration and even before open source intelligence and reconnaissance. We are coming to the point where there is a lot of different systems. We have somehow mapped the network. We have identified the classes of operating systems that are running on the hosts, and at this point we have to deepen our understanding of what kinds of operating environments are within these hosts with these operating systems, and then attempt mounting practical attacks, right? So the ones that are normally executed against legitimate businesses and people in the wild, right? So we will start from Windows and different classes of attacks that can be executed against this operating system, since it's still the most prevalent in the business world. And then we will review what's going on in the Linux world, how it's different from Windows, and what are similarities, and so on. So first let's review Windows architecture and the theory, basically, right? So how attacks work and what can prevent them, and what security controls we have to circumvent in order to successfully attack Windows systems. So first of all, let's review the architecture. So as you already know, most probably, right, because virtually everyone had some experience with Windows operating systems in their life. There are certain specifics to Windows architecture, right? So the process of Windows startup is called bootstrap, and it's virtually, it can be imagined as the system pulling her own straps, right, in order to start first the master boot record and then identify a bootable partition on the disk, and then on this partition find the file that indicates where the code, the system code, is located, and then read that code into the memory and start execution, and so on. So it is coming from the very low level of architecture, from the BIOS, the so-called firmware, right, more in general, that is predefining what's going on next, and each next level of booting process is in fact explicitly and fully trusted by the next step, right? So for example, the firmware explicitly trusts the hardware. Okay, so you can imagine that if you have a backdoor on the hardware level, no matter how many times you rewrite your BIOS firmware, you will still be compromised. Okay, and next after the BIOS, you see how operating system boots up, relying on the data in CMOS, right, in the persistent memory that BIOS uses, right, for its configuration. And the next layer, operating system, trusts BIOS, trusts firmware, which in turn still trusts the hardware, and so on. Yeah, so this is the overall concept of what's going on in Windows world, and actually it's pretty much the same over all the architecture types. Yeah, so after you have successfully boot the operating system, you will start some process or user sessions, interactive or automated, and all of them will have some permissions, will share the memory, will store something on file system. It will be represented as processes running in memory and operating over files, network sockets, and so on, right? So every process will explicitly trust the operating system, which will trust the firmware, and so on. So this concept of each next layer, each higher layer trusting all the above layers is very important, right? Because this is basically how trust is built in the operating environment. Once you compromise something below, at the below level, you will be able theoretically and most probably practically to compromise everything that is above it. For example, you might be familiar with the virtualization environments, right? So there could be many operating systems running on one physical machine if it's using some kind of hypervisor software in order to virtualize the environments of its virtual machine, its guests, right? So let me give you an example. If you have administrative access, and in some cases even admin access is not required, only like user level access to hypervisor is enough to compromise, to fully compromise all its guests. Okay, and I can tell you that this happens a lot, right? In business environment, there is normally some kind of an operating server room. Yeah, so there is virtualized environment, and it runs on a bunch of hypervisors that is in turn managed by a standalone controller or a private cloud setup like CloudStack or OpenStack or whatever. And all this is poorly configured, and once you get into the controller, you can easily siphon through the configuration to get to hypervisors, and on hypervisors you can, I don't know, just install an ISO, a virtual CD-ROM, to an existing virtual machine that is, let's say, a domain controller for the organization. Okay, and you just reboot this domain controller and you get booted up from the CD you control, right? You provided the new operating system for this virtualized environment, and you can do whatever you want. You can change passwords, you can read, write files, and so on. So and there is a tool for that. There is a commercially available tool you can use for just this purpose, and this was actually a totally realistic example I personally have executed once on a penetration test. More than once, actually, but yeah, for this example, I think that one case would be enough. So remember that there are these layers of architecture. Each of them is explicitly trusting all the above levels. Okay, so how the things are organized on the physical and virtual representation of objects in the system. So everything that's dynamic is normally run as processes or threads within a process. Yeah, so once an executable is run by the operating system, it is normally inheriting the permissions of a user that has started this process, and all the other processes will fork, yeah, will be started by this process with the same permissions. Yeah, and they will have, for example, access to all file system objects, to all directories and files that are set to be accessed by this user, by this specific user that has started the process. And these processes will have some memory segments dedicated to them. So normally these will be isolated memory segments. Sometimes they can be shared. This is done more. This is done normally as a hack to increase the interoperability of different processes, and this is normal for highly intensively used environments and is not frequently met on desktop operating systems or general purpose servers, right? And these permissions are strongly tied with with protection rings, with this concept of protection rings. So theoretically, there are 4 of them, right, starting from 0 to 3, and you can imagine that is multiple rings that are having one common center, and the inner ring, ring 0, runs virtually runs the kernel, right, the most highly privileged process in the system. Then ring 1 is wider, and it runs some high privileged device drivers, right? And then outer ring 2, runs some low privileged device drivers, and then the outmost ring 3, it runs all user-land, so-called user-land utilities that are run by normal users. Yeah, so all these things can be run with super privileges, like get directly into ring 0, but this ring 0 is normally dedicated to the kernel and to the services that are run by the super user, by the system administrator existing in the operating system. Yeah, so that's really a high-level concept that is implemented in different systems very differently, but you can imagine that as there is a ring 0, and you as a hacker should always aim for that center of these protection rings, right? So ring 0 is your ultimate goal in a local system. Okay, so permissions are organized in the roles that are normally assigned to groups, and users are the members of those groups. For example, if you want to have super user permissions on a local machine, you normally have to be the member of administrators group. Yeah, so local administrators group, or you have to be a member of a group that is a subgroup of local administrators. So this means that it can be really hierarchical, and there could be different levels, but in the end you have to be a local admin, and this is a real problem, right? So users having access as system administrators to their local machines is it's happening a lot in enterprise environments. Why? Frankly, I don't know. So maybe there is just a lot of work for desktop teams to do, and they assign like advanced users, power users having experience and skill to administer their own laptops these permissions in order just to get rid of most problems they generate, or some other reasons, I don't know, but this happens a lot, and this may result in many nasty things. For example, if something is run with this super user in the system, yeah, and it's a highly sophisticated program, and this software, let's say it's old and not very up to date, and let's say it's web browser, okay, so it's like an outdated Firefox that has some remotely exploitable vulnerability in it, and you can specifically craft the exploit, post it on the web page that is frequently visited by the user, or just attract the user to the website you specifically have prepared for this purpose. And yeah, you just get this Firefox to your web server, and you're done. Okay, you have remote access, and then you can perform some post-exploitation actions, perform lateral movement and collect information, and then progress into the network that the user is currently connected to. So this is how it normally happens. But this becomes more and more rare, and this is a good thing. More and more IT environments are forced to use this multi-purpose user accounts of different permissions assigned to them. Like for interactive login to operating system, you have a normal user account, and then in order to run something with elevated permissions, you have to run it as a different user. Or as Microsoft has decided that most probably this advice to compartmentalize the permissions between different users will not work anyway, right? Because people, in the end, people are just lazy, and they will use the account with the highest permissions for all the purposes. They have invented this UAC thing, yeah. So user access control, I guess it's its name. So they control the use of the actual permissions, yeah. So there are granular permissions for different actions. So for login, for example, we have one type of permission. It's like local login permission. For running programs with local administrator rights, there is a different permission. For reading or writing system files, there is yet another permission. And every time you try to switch to using this permission, to add this permission to your current session, you are forced to confirm that in this pop-up window that sometimes even blocks all the other windows in order not to be easily exploited. So this is like a trade-off. Yeah, it's still a permission management, but it's more technical, and basically it has been first introduced to OS X, right, to Apple products, but then Microsoft thought that this is a good paradigm and they have to use that as well. So this is how the overall Windows security architecture looks like. Yeah, so there are these horizontal things, the rings, and there are this vertical scale. There is this vertical scale of different layers of architecture, each of them trusting the below levels. Yeah, lower levels.